Now viewers, a plane is determined uniquely if the normal to the plane and its distance from the origin are given, right? Now here consider a plane whose perpendicular distance from the origin is d, and let us take a plane like this. This is a plane, and let us take the distance of this plane from origin is say d, right? So let us take the distance as ON, right? Now let us take any point P on the plane, and say the coordinates of this point P are x comma y comma z, and ON is the normal to the plane, right? So ON vector is normal to the plane or perpendicular to the plane, normal to the plane. And let us say this point is A, this is B, and this is C, and ABC is our plane, right? This is our plane. Now let us join PN and OP, right? Now OP is the position vector of this point P, and this is equal to vector R, right? Let us say this is vector R, and ON is the normal to the plane, and let n cap is the unit vector, n cap is the unit vector along ON, right? Along the vector ON, right? Okay, now from this figure we see that this vector Pn or Np, we can say Pn is equal to On minus Op, right? From the triangle law of addition of vectors. So On is the normal vector to this plane, right? And let us say On is equal to d times n cap, where d is the distance of the plane, from the origin, right? And the origin is the point O. So we can say that the magnitude of vector On is equal to d, since the vector magnitude of vector n cap is 1, right? Now let us come to this point. Here we have vector Pn is equal to vector On minus vector Op. Now vector On can be written as dn cap, and vector Op is vector R, right? Now we know that this On vector is perpendicular, it is perpendicular to every line which lies in that plane, right? Now see this vector On is perpendicular, this is perpendicular to every line which lies in the plane A, B and C. Okay, so therefore we can say that On is perpendicular to vector Pn. Now from the concept of dot product of two vectors, we know that if two vectors A and B are perpendicular, then their dot product should be 0. Or we can say that their scalar product is 0. Now ON vector is perpendicular to PN vector, so ON vector perpendicular to PN vector, so therefore vector ON dot PN vector is equal to 0. Now what is ON? ON is dn cap dot, and what is the vector Pn? Pn is vector dn cap minus r cap, it is r vector, right? And this is equal to 0. Now since d is a scalar, so this vector equation becomes n cap dot dn cap minus vector r is equal to 0, right? Now if we take the dot product of these two vectors, we get d times vector n cap dot n cap minus n cap dot vector r is equal to 0. Now n cap dot n cap is equal to 1, right? So therefore we have d times r dot n cap is equal to 0, because the dot product of two vectors is commutative. Now this can be written as r dot n cap is equal to d. So this is the vector equation of a plane in normal form. Right? Now viewers, thus we have derived the normal form of the vector equation of the plane. So here this is a plane, and let us denote the plane by pi, or we can denote it by some other alphabet and say this is a plane S, and the vector equation is r dot, that is vector r. Vector r is the position vector of any point P lying on this plane and having the coordinates x, y, z, and we take the vector dot product of vector r with the normal vector, the unit vector along the direction of the normal vector n. So here we have n cap, and this is equal to d, where d is the distance of this plane from origin, right? So here's this is the vector equation, and let vector r be written as xi cap yj cap plus zk cap, and let n cap is equal to li cap plus mj cap plus nk cap, where L, M and N are the direction cosines of the normal vector, vector ON, right? So therefore this equation can be written as, or it can be expressed in Cartesian form as xi cap plus yj cap plus zk cap dot n cap is li cap plus mj cap plus nk cap is equal to d, right? Now taking the dot product of these two vectors, we get Lx plus My plus Nz equal to D, right? Taking the dot product of these two vectors, we get Lx plus My plus Nz equal to D. So this is the Cartesian form of the equation of a plane, and where L, M and N are respectively the coefficients of x, y and z, and L, M, N are the direction cosines of the normal vector to the plane, provided here we also have the condition that L square plus M square plus N square should be equal to 1, and D is the distance of the plane from origin, right? Now viewers, here we have one more important thing to discuss. See, from this vector equation, we know that any vector A cap can be written as vector A divided by the magnitude of vector A, right? So here we have the unit vector which is along the direction of the normal vector. So n cap can be written as vector n, this is vector n, and divided by the magnitude of vector n, right? So this is the unit vector along this direction n vector. Now if we substitute this value here, we get okay, so we get vector r dot vector n divided by the magnitude of vector n is equal to D. So this equation can also be written as vector r dot vector n is equal to D times of the magnitude of vector n, right? Since these two are scalars, so let us denote the product of these two scalars by, say, scalar p. So therefore the normal form of the vector equation of a plane can also be expressed as vector r dot vector n is equal to p, right? Now viewers, let us take this important problem. Here we have to find the vector equation of a plane which is at a distance of 6 divided by square root of 29 units from the origin, and its normal vector from the origin is 2i cap minus 3j cap plus 4k cap, and also we have to find its Cartesian form. So let us take this as the plane, and let the unit, the normal vector, say this is the normal vector, and this is vector n, and we are given here the vector n as 2i cap minus 3j cap plus 4k cap, right? And let us say this is point to say n, and we are given on, right? And on is the distance of this plane from the origin, and that is 6 divided by square root of 29, and this is actually our D, right? So we know that the normal form of the equation of the plane is vector r dot n cap is equal to D, right? Now here we are given the vector n, which is the normal vector to this plane, but here we have the unit vector. So the unit is equal to vector n divided by the magnitude of vector n. So this can be written as 2i cap minus 3j cap plus 4k cap and divided by the square root of 2 square plus minus 3 square plus 4 square. So this vector, the vector n cap is equal to 2i cap minus 3j cap plus 4k cap divided by square root of, this is 16 plus 9, that is 25 plus 4, 29, right? Now viewers, we have r dot and r vector dot n cap is equal to d. So here we substitute the values of n cap. So we have 2i minus 3j plus 4k divided by square root of 29 is equal to 6 over square root of 29, right? Now this can also be written as r dot 2 divided by square root of 29 I cap minus 3 divided by square root of 29 j cap plus 4 divided by square root of 29 k cap is equal to 6 over square root of 29. So this is the vector equation of the given plane, right? Now for obtaining the Cartesian equation of the plane, we will take the help of this vector equation. See here, square root of 29 and square root of 29 get cancelled, and we have r dot 2i cap minus 3j cap plus 4k cap is equal to 6, right? Now what is vector r? Vector r is xi cap plus yj cap plus zk cap and the dot product with the vector 2i cap minus 3j cap plus 4k cap is equal to 6, right? So if we take the dot product of these two vectors, we get the product of the I component, J component and KK component, right? So here we have 2x, then we have minus 3y, and then we have 4z, right? That is equal to 6. So this is the Cartesian equation of the given plane. Now viewers, here I would like to mention an important point, that the Cartesian equation is given by, see, this is given by r dot 2i cap minus 3j cap plus 4k cap divided by square root of 29 is equal to 6 over square root of 29. So this is the vector equation, right? And the Cartesian equation is 2x minus 3y plus 4z is equal to 6, right? Now here we conclude, or we can make some important conclusion, And the first conclusion is that whenever the equation of a plane is given in this form, right? See, this is the Cartesian form of the plane, and this equation shows that the general equation of a plane is of the form ax plus by plus cz is equal to d, right? So here the Cartesian equation is 2x minus 3y plus 4z is equal to 6. Now if we compare both these equations, we see that the direction ratios of the normal are 2, minus 3 and 4, right? Or in general we can say that the coefficients of x, y and z respectively are the drs of the normal to this plane, right? So a, b and c are the drs of this plane, right? So the drs of this plane are 2, minus 3 and 4. And if we divide both sides of this equation by square root of a square plus b square plus c square, then we get the direction cosines of the plane, right? So if we divide both sides by this factor, then we have a divided by square root of a square plus b square plus c square, x plus b divided by square root of a square plus b square plus c square, y plus c divided by square root of a square plus b square plus c square, z is equal to d divided by square root of a square plus b square plus c square. Now this term is equal to L, and this is Lx, plus this term is m, so this is my, plus this term is your n, and this is nz, equal to d divided by square root of a square plus b square plus c square becomes the quantity small d. So here L, m and n are the direction cosines of the normal, while this d is the distance of the plane from the origin, and d is given by this expression, that is capital D divided by square root of a square plus b square plus c square, right? Now viewers, let us consider the equation of a plane as 3x plus 2y minus z equal to 5. Now this equation is of the form ax plus by plus cz equal to d, right? So this is the general equation of a plane, and here a, b, c denotes the direction ratios of the normal, right? So here a, b, c are the direction ratios of the normal to the plane ax plus by plus cz equal to d, right? So here if we compare these two equations, then the drs of the normal are 3, 2 and minus 1. Here we will have 1, So we have 3, 2 and minus 1. Now in order to obtain the direction cosines, what we will do, we will find the expression at the square root of 3 square plus 2 square plus minus 1 square, and this is equal to 9 plus 4 plus 1, and this is square root of 14. And if we divide each of these numbers by square root of 14, then we get the direction cosines of the normal. So direction cosines are 3 divided by square root of 14, 2 divided by square root of 14, and minus 1 divided by square root of 14, right? So drs we have obtained, dc's we have obtained. Now this is the Cartesian equation, and suppose we divide both sides of this equation by this number, we get 3 by square root of 14 x plus 2 by square root of 14 y minus 1 over square root of 14 z is equal to 5 divided by square root of 14, right? Now this Cartesian equation can now be converted into the vector equation, and we can write vector r dot 3 by square root of 14 I cap plus 2 by square root of 14 j cap minus 1 over square root of 14 k cap, right? And this is equal to 5 divided by square root of 14. Now viewers, if we compare this vector equation with this equation, then we see that the unit vector along the normal to the plane is given by this vector, and the distance of the plane from the origin is 5 over square root of 14, right? Now viewers, let us consider this system of mutually perpendicular coordinate axes, and here we see that these three axes are mutually perpendicular to each other, right? Now we see that here if we draw a parallel line, say like this, then we see that this is our XOZ plane, right? So this is our XOZ plane, and we can have our XOY plane as this plane, right? So this is our XOY plane, and here we have our YOZ plane, right? So if we write, if we draw a line which is parallel to OZ, then we have our ZOY plane, right? Okay. So here's here XOZ plane, then we have XOY plane, and then we have ZOY plane, right? Now here we see that OY is perpendicular to XOZ plane, and OZ is perpendicular to XOY plane, and OX is perpendicular to ZOY plane. Therefore, for XOZ plane, for this plane OY or the y-axis can be taken as the normal vector. Similarly, for x or y plane, uh, the z-axis or OZ can be taken as the normal vector, and for z or y plane, OX or x-axis can be taken as the normal vector. Now viewers, we know that the direction cosines of y-axis are 0, 1 and 0, right? The direction cosines of z-axis are 0, 0 and 1, and the direction cosines of x-axis are 1, 0 and 0, right? Now viewers, if we wish to find the equation of x or z plane, then we know that any point which lies on x or z plane has y coordinate 0, right? So therefore the equation of x or z plane is y is equal to 0, right? Similarly, the equation of x or y plane is z is equal to 0, right? So here we have z is equal to 0, and the equation of z or y plane is x equal to 0, right? Now this equation, that is equation of x or z plane, is y is equal to 0, which can also be written as 0x plus 1y plus 0z is equal to 0, right? Similarly, z equal to 0 is the equation of x or y plane, which can be written as 0x plus 0y plus 1z equal to 0, right? And the equation of z or y plane is x equal to 0, which can be written as 1x plus 0y plus 0z equal to 0, right? Therefore, we have represented the equation of these three planes in the form of ax plus by plus cz equal to d, right? Now let us write the equation of these three planes in vector form. Now the vector form of the equation of x or z plane is we can write it here, that is r dot j cap is equal to 0, right? So r vector r dot j cap is equal to 0. Now the vector equation of x or y plane is r dot k cap is equal to 0, and the vector equation of z or y plane is r dot I cap is equal to 0. So viewers, the vector equation of this plane is r dot j cap is equal to 0. The vector equation of this plane x or y is r dot k cap is equal to 0, and the vector equation of z or y plane is r dot I cap is equal to 0. Now viewers, these three vector equations represents that the distance of these planes from origin is 0, right? For example, the plane x or y, the equation is vector r dot k cap equal to 0, and here if we compare these three equations, with the standard equation of a plane, that is vector r dot n cap equal to d, then this d represents the distance of the plane from origin, and c in case of these three planes the value of d is 0, right? Okay, now there is one more important point to discuss. The point is the intersection of, see, the intersection of this plane, that is x o z and x o z and say y o z plane is a line, and the line is this line, that is the z-axis. Clear? So this plane and this plane, that is plane XOZ and the plane YOZ, they both intersect in a line, and the line is z-axis, right? The line is z-axis. Similarly, the plane XOY and YOZ, these two planes intersect in a line, and the line is y-axis, right? The line is y-axis. And similarly, the plane XOZ and XOZ and XOY, these two planes intersect in a line, and the line is x-axis. Clear? Okay, so what we have concluded from this discussion, that whenever two planes intersect, they intersect in a line, and the line is called the line of intersection of planes, right? So in case of XOZ plane and YOZ plane, the line of intersection is z-axis. Similarly, in case of XOY and YOZ, the line of intersection is called y-axis, and similarly in case of XOZ and XOY plane, the line of intersection of planes is known as x-axis.